Hey guys, welcome back to another lecture video for Chem 115. In this lecture video, we will discuss how we can manipulate multiple chemical reactions to determine the overall equilibrium constant, Kc, for the net chemical reaction. So the example I want to use to better understand this topic is the synthesis of acetaminophen, which happens to be the active ingredient in Tylenol. Now, it turns out that we can synthesize acetaminophen, which is this substance that I'm circling in blue, in 3 steps. To begin, we're going to be using phenol as our starting reactant, and phenol is going to be represented by letter A. And so in the presence of dilute nitric acid, this phenol is going to undergo an electrophilic substitution to produce this specific substance, which I'm going to label as product B. And so the completion of the first step will allow the product of the first step to become the reactant of the second step. And so this substance B, is then going to undergo a reduction process that allows this nitro group to be reduced to NH2. And so product C then becomes the reactant in a third step. And after reactant C reacts with this anhydride, then the final product will be produced, which is acetaminophen. So overall, we can go ahead and summarize this sequence of chemical reactions as simply A converted to B, B converted to C, and C converted to D. And so for multiple chemical reactions, we have multiple equilibria in which the rate constants of the forward and the reverse direction in each step is going to be different from each other. And so, for instance, the rate constants in the forward direction in the first step, second step, and third step are all going to be different values because they're different chemical reactions. The same can be said about the reverse reaction for the first step, the second step, and the third step. Now, because all of these rate constants are different, then that means that their equilibrium constants are also different. And so step number 1, the equilibrium constant can be represented as Kc1. So this is the equilibrium constant for the first step. For the second step, I can go ahead and label the equilibrium constant for the second step as Kc2. And for the third step, it'll be Kc3. And so if we wanted to summarize what's happening in this sequence of chemical reaction, I can simply add all of these individual steps up. And when I start adding these individual steps, I'm going to be canceling any intermediates. And so the sum of all 3 of these steps to produce acetaminophen allows substance B and substance C to be canceled. Thus, this leaves us with substance A, which is our phenol, in equilibrium with a production of substance D, which is going to be acetaminophen. And so when we add all 3 of these chemical reactions, then what do we do with the equilibrium constants? And so the equilibrium constant for this overall chemical equation is going to be different than the equilibrium constants for each and every single one of the individual steps. And so this is going to represent the overall chemical equation. And Kc overall, I'll put this in parentheses, is once again going to be unique and different than all of these equilibrium constants for each step in the chemical reaction. And so what we want to learn in this section is how to manipulate these chemical equations, and in doing so, manipulate the equilibrium constants for each of these individual steps, and how to combine these equilibrium constants to be able to calculate the overall equilibrium constant, which represents the overall chemical equation. All right, so now that we have the purpose of this specific lecture topic, let's go ahead and look at some tools that will allow us to manipulate chemical equations. So manipulating chemical equations is something that you guys should have been exposed to in the first semester of general chemistry. And so you guys manipulated chemical equations when you guys were talking about Hess's law in the thermochemistry chapter, for instance. Anyways, let's go ahead and look at the first tool that we want to put in our bag. So let's just say that you wanted to flip a chemical equation. If you flip a chemical equation, what do you do to the equilibrium constant? Well, in this case, we're going to take the reciprocal of the equilibrium constant, and we'll see why in just a second. So let's just visualize this process first. And so here we have reactant AB producing product CD. And so in our process of manipulating these chemical equations so that it looks like the overall chemical equation, we might have to flip some chemical equations such that product CD now becomes reactant CD and reactant AB now becomes product AB. And so if you take the mass action expression of this chemical equation, then notice that AB, which is our product after we flipped it, now goes in the numerator, where AB in the original equation was a reactant, which went in the denominator. And so because we flipped the positions of the reactants and products in this ratio to, in this mass action expression, which defines the equilibrium constant, then that means that we simply have to take the reciprocal of the equilibrium constant Kc, and that will represent the flipping of this chemical equation. All right, so long story short, if you flip the chemical equation, you must take the reciprocal of the equilibrium constant Kc. All right, so let's go ahead and talk about what we need to do to Kc if we multiply or divide the chemical equation by some factor. And so if you multiply a chemical equation by a specific value, then that value will be used as the exponent for the equilibrium constant. And so let's go ahead and better understand why. So let's just say that we have A plus B producing C and D, and the ratio is 1, 1, 1, 1. And so let's just say that we want to multiply everything by a factor of 3. So this is going to be the factor that we're going to be using to multiply the coefficients in this entire chemical equation. And so what we get, the result, is 3A, 3B, 3C, 3D. If you recall, in the mass, when you take the mass action expression of the result, it's simply going to be the ratio of the concentration of the products raised to the coefficient over the concentration of the reactants raised to their coefficient. And so here in this case, notice that if we raise each of these concentrations by their coefficient, we get something that looks like this. And so we can expand this by repeating it 3 times. And so therefore, Kc needs to be raised by that same power. Okay? And so if we're multiplying a chemical equation by a specific factor, that same value will be used as the exponent for Kc. Okay? So if we multiply by 3, we're going to raise Kc by 3. And so let's go ahead and take a look at what we're going to be doing, or what we need to do when we divide a chemical equation by some factor. And so overall, if we're dividing the chemical equation by some factor, we must take the root of the Kc, the equilibrium constant, by that same value. And so what do I mean by that? So if this was what we started with, and let's just say that in the course of the manipulation of our chemical equations, it involves us trying to divide that chemical equation by 3. And so if we divide this by 3, divide this by 3, divide this by 3, divide this by 3, we essentially get 1, 1, 1, and 1. And so we're going to go ahead and take the root of that value for Kc. And so we're going to take, so since in this example we're dividing it by 3, we're going to take the third root of Kc. Oops. And whatever this value is, so let's just say this is Kc nu. Okay. So the new equilibrium constant after the manipulation is the result of taking the third root of the equilibrium constant. Now, if you guys don't have this function in your calculator, another way that you guys can represent the third root of Kc is by putting the value of Kc in parentheses, and then in your calculator use the caret sign, and then perhaps add in another parentheses and put in 1 divided by 3. Okay, and so let me clean this up. So let's see what this looks like. So it's Kc raised to the 1/3 power, basically. And so this is what you guys are going to plug into your calculator if you don't happen to have the third root function available to you. Okay. Now, if you're dividing the value by 2, that means you're going to take the square root of Kc. If you're dividing the value by 4, for instance, you're going to take the 4th root of Kc. If you're dividing by 5, take the 5th root. You guys hopefully see the pattern here. And so you can go ahead and plug it into your calculator if you don't have these higher roots as parentheses Kc over 1/2, or raised to the 1/2 power, Kc raised to the 1/4 power, Kc raised to the 1/5 power. Okay. So once again, if you guys don't have these roots in your calculator, you guys can just take the value of Kc and raise it to this specific exponent. But you guys definitely do need your exponent, your caret sign in your calculator. All right, so one last tool that we need to go over before we go through some examples So let's just say that we've done all of our manipulations, and the only thing that's left for us to do is to basically add all of the chemical equilibria, add all of the chemical equations. And so if we add all the chemical equations, we need to multiply the equilibrium constant for each of the reaction that was added to represent the new equilibrium constant for the overall chemical reaction. So what do I mean by this? So let's just say that this is reaction 1, this is reaction 2, and let's just say that we're going to add reaction 1 and reaction 2. And so when we add the reactions, whether it's 2 reactions, 3 reactions, 4 reactions, whatever, any substances that are on the right hand side and the left hand side of the arrow in in different chemical reactions, they're going to cancel. So we saw this when we were talking about reactive intermediates in kinetics. So basically we're canceling our reactive intermediates. You guys should have been exposed to this concept as well in thermochemistry in the first semester of general chem. And so basically whatever does not cancel is going to be what's written on the reactant side. Whatever doesn't cancel over here is going to be written on the product side. And so this is going to represent the overall chemical equation when all the individual reactions were added. And so to represent this equilibrium constant, Kc overall, what we need to do is multiply the individual equilibrium constants that represents each of these individual reactions. And so the product of the individual rate constants, oh, not rate constants, why am I saying that? Equilibrium constant, I apologize. The individual equilibrium constant. Too many K's here. Individual equilibrium constant. Okay, so the multiplication or the product of the individual equilibrium constant is going to give us the overall equilibrium constant that reflects this overall chemical equation. All right. So we now have all of the tools that we need to do some practice problems. All right, let's go ahead and look at the first one. So we're going to go ahead and use this data to calculate the equilibrium constant for the following reaction. So notice that here we have reaction 1 with an equilibrium constant of 5.40 times 10 to the negative 3. And here we have another reaction with an equilibrium constant of 1.2 times 10 to the positive 7. So the combination of these two individual chemical reactions will allow us to produce the overall chemical equation. And by taking into consideration the manipulations of the equilibrium constants, we should be able to determine the overall equilibrium constant for this overall reaction. Okay, so this is basically what we're searching for, the equilibrium constant for the overall reaction. All right, so to do this, the best way to do this, or how I typically do this, is I use the overall chemical reaction to help guide me in my manipulation. And so what do I mean by that? Well, my first reactant that I see is CH4. And so what I'm going to do is I'm going to search for all of the CH4s that's present in all of these individual chemical reactions. So notice that this CH4 is on the reactant side of the overall chemical equation. And so that means that I want my CH4 to also be in the same position. And it is. And so if it is, then we don't really need to change it. And we're not going to change it. We're not going to do any manipulation. So we're going to skip over to the next substance. Well, the next substance that I see is CO2. And once again, it has to be on the reactant side. And so if I look at both of these individual chemical reactions, I observe that there are two CO2s that are present. Now, looking at their positions with respect to the equilibrium, notice that they're on opposite sides of the arrow. And so what that means is that if we add both of these equations, then this CO2 is going to cancel with one of these CO2s, leaving you with only one CO2 that's present on the reactant side. And so that carries down. Okay, and so it looks like the manipulation that I'm going to have to do is adding all of these individual chemical reactions. And so now that we preemptively can see that this CO2 is going to be on the reactant or the left-hand side when we add both of these equations, we're going to go ahead and move on to the next substance. And in this case, CH2CO is found on the product side. And if I search for CH2CO, I see that it's right here and it's also on the product side. So it's going to be carried down. It's on the correct side of the arrow and we have the correct number. It's 1 and 1. Okay. Last but not least, we have H2O. So looking at both of these two chemical equations, I see H2O in two places, one here and one here. And so notice that the positions of these water vapors are on opposite sides of the arrow. And so that means that if I were to add both of these chemical equations, then these guys will cancel, leaving me with just one water vapor, which carries over in the product side. Okay, and so it looks like if I were to add these two chemical equations, then my carbon dioxides are going to cancel, leaving me with one CO2 on the reactant side. And then my water is going to cancel, leaving me with one H2O on the product side. And so the last item that is not talked about between these two, but it's not present in the overall chemical equation, is oxygen gas. So notice how here I have two oxygen gases and two oxygen gases. But since both of these oxygen gases are on either side, we're going to consider that as a quote-unquote reactive intermediate, and therefore it'll be canceled. And so I'm simply just going to carry on over the remaining substances that were not canceled. And notice that I get the same exact chemical equation that the question is prompting me to obtain. And so for this example, it turns out the only manipulation that was required was the addition of the two chemical reactions. Okay. And so since we're adding the two chemical reactions, what that means is that we must multiply KC1 and KC2. Okay, and so this equilibrium constant refers to the first reaction. So I'm going to say that this is KC1. And then this equilibrium constant refers to the second reaction, that's KC2. And so if I add two chemical reactions to produce an overall chemical reaction, that means I need to multiply the individual equilibrium constants. And so Kc overall equals to the product of Kc1 and Kc2. And this value is going to be 5.40 times 10 to the negative 3 times that by 1.2 times 10 to the positive 7. So I'm going to go ahead and plug that into my calculator real quick. I encourage you guys to do the same. So 5.40 times that by 10 to the negative 3 times that by 1.2 times 10 to the positive 7. And so since I have two sig figs here, I'm going to report two sig figs in my final answer. So I have 6.5 times 10 to the positive 4. And so that's going to represent my overall Kc. Oops. Okay. And so overall, what is this telling me? This is telling me that if my overall chemical equation is methane reacting with carbon dioxide to produce this substance, I believe this substance plus water vapor, the equilibrium constant for this specific chemical reaction is going to be 6.5 times 10 to the positive 4. And so if you recall, I'm just going to link up a concept. Since Kc is 6.5 times 10 to the positive 4, Kc is going to be far, far greater than 1. So what this is telling us is that the equilibrium is going to lie to the right. In other words, once equilibrium is achieved, it's going to favor the production of products. Therefore, at equilibrium, there should be a higher concentration of products than reactants. Okay. So let's go ahead and take a look at one last example here. So we have two chemical reactions. We have this chemical reaction with this specific equilibrium constant. And so I'm just going to go ahead and put in Kc1. And then I have this second chemical reaction with this specific equilibrium constant. So I'm going to put that as Kc2. Okay. And so what I want to do is calculate the overall equilibrium constant. So this is going to be Kc overall, much like what we did in the previous example for this chemical reaction. All right. And so what I'm going to do is I'm going to start, I'm going to use the overall chemical reaction as my point of reference, if you will. So I'm going to allow my overall chemical reaction to guide me in my manipulation. So what that means is that I'm going to look at the position of this first substance, NaCl, and see where it's found between both of these individual reactions. And notice that I see that it's on the right-hand side, it's on the product side of reaction 1. And I also want you guys to take a look at the stoichiometry. there's two NOCLs. And in this scenario, there's only one NOCl that's represented. So it doesn't really cancel out with anything else to reduce this number from 2 to 1. Okay, so this is telling me that I have to do two things. First, since NOCl is not on the correct side in the overall chemical reaction compared to reaction 1, I need to flip. Let me see here. You know what? Let's just do this step by step. So let's just flip first. Okay. So notice that these guys are on the opposite side. So the first thing that I'm going to do is flip. I'm going to go ahead and use a different color here. Let me go ahead and use gray. See how that works. So hopefully you guys can read this. So I'm going to go ahead and flip this chemical equation. And if I were to flip this chemical equation, then I get 2 NOCl. And for the sake of time, I'm not going to write the physical states of matter. I guess I'm just being lazy. I guess I'll just write it. 2 NOCl. Oops. And when I flip the chemical equation, then I get 2NO and Cl2 gas on the product side. And so remember, when you flip the chemical equation, what must you do to the equilibrium constant for that reaction? Okay, so you must take its reciprocal. So therefore, Kc is going to, so we're going to take the reciprocal of Kc. So it's going to be 1 over, what is it, 3.2 times 10 to negative 3. All right. And so now if you compare the overall reaction to what we currently have, notice that we still have 2 NOCl, but here there's only 1 NOCl. And so that's going to prompt us to divide, to do another manipulation, such that we're going to divide the entire chemical equation by 2. And so for the sake of time, I'm just going to go ahead and duplicate this. And then I'm going to go ahead and divide this by 2, divide this by 2, divide this by 2. Now, anything that you don't see, you're going to assume that there's a 1. If you're going to write Cl2, then there's at least 1 Cl2. And just to simplify this, 2 over 2 is 1, 2 over 2 is 1, and what I have left is just 1/2 Cl2. Okay. All right. And so if you recall, if you were to divide the equilibrium, or if you were to divide a chemical equation by a factor, then you need to take the root of that factor and apply it to Kc. And so here, since Kc is 1 over 3.20 times 10 to the negative 3, then dividing it by 2 tells us that we have to take the square root. So Kc1 is changing once again. And so overall, I'm going to duplicate this. The value of Kc, or Kc1, for after manipulating both these, after performing both of these manipulations, I'm just going to punch this into the calculator real quick. So square root of 1 over 3.20 times 10 to the negative 3. That's going to give me a very big number, so it's going to be 17 point, not a big number, but so there's a whole lot of decimals, so 17.677 0.6695. The list goes on. So 3 sig figs. 3 sig figs. Okay. All right. So that's pretty much it for NOCl. And so if you guys look, we have NOCl on the left, NOC on the left, and it turns out this manipulation also allows us to get 1/2 Cl2. Okay, so we kind of hit two birds with one stone. And NO is not in this chemical reaction, so therefore we're done with reaction 1. So let's go ahead and look at reaction 2. I want you guys to notice that this oxygen in the overall chemical reaction is on the left-hand side, but it's on the right-hand side in reaction 2. And so that's going to prompt me that I need to take this oxygen and move it to the left-hand side. In other words, I need to flip the chemical equation. All right, and so my first manipulation is that I'm going to flip this chemical equation to give me, I'll go ahead and write this one in green. And so if I flip this equation, I have 2NO gas state plus O2 gas state to produce 2NO2. And so since I flipped my chemical equation, Kc2, this 15.5, I need to take the reciprocal of this when I flip the chemical equation. Okay. All right, so notice how my O2 is now on the left-hand side, which is awesome because it's now looking like my overall chemical reaction. However, there's a problem. This is 1/2, but this is 1. And so this is going to prompt me to do another manipulation. And the second manipulation involves dividing this chemical reaction by 2. So I'm going to go ahead and take this guy, duplicate it, and I'm going to divide everything by 2. Okay. And so I'm going to go ahead and duplicate this here. And so I'm going to simplify this. So this is gone, that stays, that's there. Awesome. Okay, cool. So, looks like I didn't carry down the gas. And so after dividing everything by 2, that means we're going to take the Kc and we're going to take it the square root of it. So I'm going to take the square root, so this is Kc2, and take the square root of 1 over 15.5. Okay. So I carried over the 15.5, and then after this manipulation, actually, you know what, let me move this up. So here's Kc2, and take the square root over 1 over 15.5. Okay. All right. And so the Kc value for the second reaction, it's going to be 1 divided by 15.5, and then I'm going to take the square root of that answer, and then that's going to give me a value of 0.254. Okay. Cool. All right, so let's see what we've accomplished after performing both of these manipulations. I'm going to go ahead and do this perhaps in a different color, green. So notice that my 1/2, probably not green, maybe this color? Sure. Probably not. Sorry, guys. Let's just stick with a good old yellow. Or actually, you know what? This bright green should be good. All right, much better. So it looks like the 1/2 O2 gas is on the correct side. And it looks like we kind of hit two birds with one stone again. Notice that NO2 is on the right side. And so this 1/2 O2 is on the left side, I apologize. And this NO2 is on the right side. Okay. Now, if you guys look at this chemical equation, both these chemical equations, notice that there's something that was not highlighted, and that's this nitrogen monoxide. So this is telling us that we're not done yet. So NO cannot be present in this chemical reaction. And so what we need to do is add both of these chemical equations so that the nitrogen monoxides can be canceled and it's not going to be represented in the overall chemical equation. And so the addition of these two resulting reactions allows the nitrogen monoxides to be canceled, and overall that's going to leave me with the overall chemical equation. So whatever is just remaining, we're going to go ahead and write it below. And it doesn't really matter who goes first, just as long as it's on the correct side with respect to the arrow. So here I have NOCl, gas, plus 1/2 O2, gas, to produce 1/2 Cl2, gas, plus NO2 gas. So all of this represents the overall chemical equation. Now, since we added, so this is a manipulation of two chemical equations, that means we need to do something to their equilibrium constants. And so if you recall, the Kc value of this is going to be 17.7. I'm just going to go ahead and round it. And the Kc value of this is equal to 0.254. So this is 2, this is 1. And so to calculate Kc overall, we're going to take Kc1 and multiply that with Kc2. And so when you do so, so I'll just put in 17.7 times this by 0.254. What value do we get? So multiply that by 17.7. I get 4.50. So the overall Kc is going to be 4.50. Okay. And so that's pretty much it. And so there's two things here. We are able to manipulate the individual chemical reactions so that we get the overall chemical equation, which is what our goal is. And so we use this overall chemical equation to help us guide the manipulation of these two chemical reactions. And whatever our manipulation is, it needs to be reflected with respect to Kc. And so the overall Kc for this overall reaction is going to be approximately 4.50. Now, you guys might get a different value if you guys were to do all the manipulations in one go. So for example, if you guys did, so if Kc overall, if you did parentheses square root of 1 over 3.20 times 10 to the negative 3 times that by square root of 1 over 15.5. So this is Kc1, this is Kc2. So I'm going to go ahead and plug that in because I think that's going to give us just a slightly different answer, and it's due to the rounding. And so parentheses square root of 1 over 3.20 times 10 to the negative 3 times that by the square root of 1 divided by 15.5. Oh no, it looks like I still got the same answer. Well, slightly the same. So it's going to be 4.49. Okay. So, whether or not you guys rounded early or you plugged everything in one go, the difference isn't too bad, right? And so both answers are acceptable at this point. All right, so that's pretty much it for this lecture video. Hopefully after going through 2 of these problems, you guys are masters of manipulating chemical equations and figuring out the equilibrium constant for the overall chemical reaction. Okay, I'll see you guys in the next lecture video.